Hello, and welcome back to a video series on MAC 1105 College Algebra. My name is Sean Perry. This is guided notes number 5 in the series on section 2.4b, completing the square. Before we begin, I'd like to motivate the method a little bit. We saw in the last section how having a square of something equal to something else is a very nice polynomial situation to have. This is because we can now use the square root property, a kind of inverse operation where we couldn't before. This allows me to solve the polynomial equation. However, in general cases with polynomials, and quadratics in particular, we're not going to be able to proceed directly with inverse operations. This is because these two are not like terms, and so we cannot isolate this square. However, if I was just able to add something to both sides of the equation, something that would allow me to factor this as a single term, x plus 1, for example, squared, well, then I have isolated the square, and I could proceed to use the square root property to solve the equation. But how did I know to add plus 1 here? To get an idea of what this special factor should be, let's consider a general polynomial, x plus b squared. This, if I FOIL it out, gives me 2bx in the middle term, and b squared as the final term. And this 2b sort of points us in the right direction. Consider, for example, if we had x plus b over 2 squared. Then I would wind up with a whole number b in the middle term. And the final term would have to be b over 2 squared. Likewise, if I had something of this form, it would factor as a perfect square in the following way. So the main idea is, say we started out with something like x squared plus cx. How could I turn it into a perfect square? Well, the factor that it's missing to become a perfect square is half of c squared. And I can't just go around adding that alone. I either have to do that on both sides of an equal sign, or I need to add and subtract it in the same move. That's what I've done here. Now this term here, x squared plus c over 2 squared, that's a perfect square. That will factor as x plus c over 2 squared. And then we have this corrective term minus c over 2 squared on the outside. Notice that it kind of turns things into a difference of squares. Now let's see how we can take advantage of this pattern to solve polynomial equations. First, we want to just practice the setup. This says determine the constants that should be added to the following binomials so that they become a perfect square trinomial. Then write the perfect square trinomial in factored form. For your homework, I believe all they want you to do here is take our middle term, 26, and we're wanting to add half of 26 squared. Now, that's of course going to be 13 squared, which is 169. I would just like to point out that even if the correct answer here is listed as 169, the manipulation we would have to do either needs to be done on both sides of an equal sign, or we need to subtract 169 in the same breath. This would then give us x plus 13 squared minus 169. Now, in the homework, if they just want a 13, great, just put a 13. If they just want this polynomial, fine, just put that polynomial. But keep in mind, we are going to have to correct our moves. It's going to be important for us to keep track of doing the same thing on both sides, or at best adding 0 to something. And here you can see that the maneuver I've done is to really just add 0 to something. I added 169, but I took it away in the same breath. Likewise, what I would want to do here is take half of negative 20, which is going to give us 10, and square it. And so really I want to add 100. I want to take x squared minus 20x and write plus 100 here. And I can really only do so if I write minus 100 afterwards, or else I've changed the line above. Although this plus is kind of leading. What should really go here? So what is this perfect square trinomial factor as now? Well, it's going to be half of this term, which is going to be minus 10 squared. And this is our factored form of the trinomial, of course, with this corrective bit out front if we were going to actually solve an equation with it. Consider the following quadratic equations. Determine the constants that should be added to both sides so that the left becomes a perfect square, then solve by completing the square. We note that we have the following middle term. That's going to be the one next to the x. This is our focus when we complete the square. What we want to do is take half of that, square it, and add it to both sides. Half of that would be minus 1, and squared would be a positive 1. So really what I would like to do is add positive 1 to both sides. On the left, this now factors as x minus 1 squared, or 1/2 the middle term going here, and then the whole thing squared. And outside we have 100, which is in fact a perfect square. This gives us x minus 1 equal to plus and minus the square root of 100, which is 10. Then we would have x equal to positive 1 plus and minus 10. 1 plus 10 is 11, and 1 minus 10 is minus 9. And these would be the two solutions for this equation. Now you might say, well, couldn't I have just brought the 99 over, set it equal to 0, and factored? Yes, you absolutely could have. It would have given you the same answers. But this will actually work for us even if we couldn't factor the equation. So in some sense, it's a more general attack than simply setting it equal to 0 and factoring, which doesn't always work. Now, let's approach this with completing the square in mind. I would like to take half of the middle term, which is positive 16, and I would like to square that. And this is the thing I want to add to both sides. Now, you might notice that 16 over 2 is 8, and 8 squared is 64, in which case it makes sense why I'm writing plus 64 on this side. I've done the same thing to both sides. Now, on one side, this is going to give us 225, and on this side, we now can factor as a perfect square. Half the middle term here is going to be the constant which goes in this position, and that's going to be positive 8, and squared. Now we take the square root of both sides. 225 is indeed a square, it's 15 squared, and so we wind up with x plus 8 is equal to plus and minus 15 squared. Don't forget the square root property calls for two answers here. This then gives us x equal to negative 8 plus and minus 15. If I add 15 to negative 8, I get 7. And if I subtract 15 from negative 8, I get negative 23. Here I have another. We take half of 8, square it, and add it to both sides. Half of negative 8 is negative 4. Squared is positive 16. And so this is what I would like to add to both sides. This now factors as x minus 4 squared, and this side becomes 36. What luck, it is indeed a square. And that does mean that this previous quadratic could have factored. We take plus and minus the square root of both sides, and we find plus and minus 6 is equal to x minus 4. Moving the 4 over to the other side as a positive, we then get 4 plus and minus 6. 4 plus 6 is 10, 4 minus 6 is minus 2. Here is another. It would seem that number 6 is a duplicate of number 5. They actually have the same numbers, so I'm not going to do it again. What I will do instead is show you what would happen if this wasn't a perfect square. That is to say, what if, instead of 20 over here, I had 21? Are we out of luck? Does the method not work? No, not at all. What we would do is still the same thing. We would take half of 8, negative 8, square it, positive 16, and we would add it to both sides. On one side now, I factor as a perfect square. On the other side, I have 37. 37 is not a square, and that really doesn't matter. We continue as such, simply writing it as a square root. Now, adding 4, I wind up with two answers. 4 plus radical 37, and 4 minus radical 37. These are the two solutions to this equation. They just happen to be irrational. In this case, the above polynomial would not factor, but still we can find two real numbers to serve as solutions. Let's continue to get some more practice in completing the square. Before we begin here, we're not in the right form. Notice that the z and the z squared have been separated. We'll need to adjust this polynomial before we begin. I do so by moving the z adjacent to the z squared, and by moving the negative 17 over to the other side. Now I can take half this middle term, which is going to be 1, or negative 1, but squaring it will make it 1. And adding 1 to this side, we get 18. This now factors as a perfect square. Z minus half the middle term, which is 1, squared, taking plus and minus the square root of each side, and bringing my negative 1 over, we get 1 plus and minus radical 18. Radical 18, well, 18 is 9 times 2, and 9 is a perfect square, so we could factor that out to simplify this as 3 radical 2. For this next one, we would like to first move the 12 over to the other side. Then we would like to add half of 8 squared, which is 16, to both sides. This now factors as x plus 4 squared, equal to the sum of these two, which is 28, taking the square root, plus and minus, and reducing to 2 radical 7 by dividing out the 4 and taking its square root. We bring our minus 4 over to get negative 4 plus and minus 2 radical 7. Again, we begin by bringing over this 19. Then we want to add 7 over 2 squared. Now this time, we're unable to deal with whole numbers only here because the middle term was not even, it was odd. That is okay. We still just need to work with the fractions. This is going to give me 49 over 4. Now, in terms of fourths, 19 times 4 will give me 76 fourths plus 49 fourths. And here I will have x plus 7 over 2 squared. 76 plus 49 is 125. So this would give me 125 fourths. Now taking the square root of both sides, I get x plus 7 halves is equal to plus n minus the square root of 125 over 4. But I can actually take the square root of 4, and in fact I can simplify the square root of 125. Bringing over my 7 halves as minus 7 halves, and simplifying this term, I wind up with 5 radical 5 over 2. And these two would be my final answer. You could take advantage of the fact that they are both written over 2 to write them as a common fraction, but I see no reason to. These are perfectly acceptable forms of the answer. Now, you might say to yourself, this appears like the kind of answers we get when we use the quadratic equation. And in fact, they are. We need to have these two methodologies sync up, or else one is not correct. In fact, the quadratic equation is produced from completing the square, which I'll show at the end of the video. Here we have a doozy. I would begin by simplifying this expression. 8 divides into each of these things. I wonder if 8 divides into 504. Just to save a little time here, it does. It is in fact 63 times 8. So I could divide negative 8 from everything, both sides. And I would here get 63, and I would here get z squared minus 2z. It's important to reduce these things first so we don't have to deal with humongous numbers. Now, half of this term would then be minus 1, and squared would be plus 1. So I add plus 1 to both sides, and pleasantly enough, we wind up with a 64 here. That's great because now we have z minus 1 squared is equal to 64, and taking the square root plus and minus, we have z minus 1 is equal to plus and minus 8. That means that z is equal to 1 plus and minus 8, which gives me either 9 from the plus or minus 7. Here's another one that's ripe for simplification. We could divide both sides by 4. Here I'd get t squared plus 2t equal to 4 goes into 14 3 times, and into the remaining 20 5 times. We could then add half of the middle term squared to each side, and we would get t plus 1 squared is equal to 36, which gives me t plus 1 equal to plus minus 6, which gives me t equal to minus 1 plus and minus 6, which gives me t equal to 5 and minus 7. Let's notice here that this entire thing reduces by 6, and let's get rid of these pesky negative signs while we're at it. This gives me z squared minus 4, or I should say plus 4. This gives me z squared plus 4z is equal to 21. We should add half the middle term squared to each side. Half the middle term is going to be 2. Squared will be 4. So this factors as z plus 2. And adding 4 to both sides, I would get 25 here. Taking the square root plus and minus of both sides and moving my 2 over as a minus 2, we get minus 2 plus and minus 5. And this is, of course, going to be minus 7 and 3. Same situation, but now I cannot exactly get rid of everything. No matter, what I really want to do is reduce the a term down to 1. That will make your completing the square far easier to comprehend. So let's first move the 2, and let's divide by 4 on both sides. Even though this doesn't completely reduce here, it's still better to have our x squared term be monic and have coefficient 1. Half the middle term is going to be 5 halves, and squaring it, we get 25 over 4. So I want to add 25 over 4 to both sides, which will give me x plus 5 halves in this case. And this is, of course, 2 fourths, and so we wind up with 23 fourths on this side. This doesn't have a nice root, at least not of the numerator, but that still gives me x plus 5 halves is equal to plus and minus radical 23 over 2. Here I've taken the square root of 4 already. Now we could bring this over and write this as x is equal to negative 5 plus and minus radical 23 over 2. Final problem. Here I would bring the 20 over. Adding half the middle term squared to each side means adding 4. And so we wind up with x plus 2 squared is equal to 24. Taking the square root of both sides, but simplifying by dividing out a 4 and square rooting it, we wind up with x is equal to minus 2 plus and minus 2 radical 6. One possible objection that students give to this method is that it seems to be extra. That is to say, it's redundant given that we have the quadratic equation. Now, it turns out, if you make it onto calculus and some later math, that completing the square as a method is useful for other reasons besides solving polynomial functions. But even if you don't take my word for that, where do you think the quadratic equation comes from? If you know the answer, you already know why completing the square is important. But I'll give you a hint. It didn't come from on high. It didn't come from angels. No oracular vision revealed it. It's just completing the square. It's completing the square on the general equation ax squared plus bx plus c equals 0. Notice that we could move our c from one side to the other. We could make our equation monic by dividing by a on both sides. We then take half of b over a, which puts a 2 in the bottom, and add its square to both sides. Now, distributing my square, I get b squared over 4a squared. On the left-hand side, we now know this factors as a perfect square. And on the right-hand side, we could combine these two fractions by multiplying on the top and bottom by 4a in order to achieve like bases. Let's clean up this fraction expression, and perhaps certain features of the quadratic equation are already being revealed. Behold the discriminant. Now we apply the square root property, but we can honestly take the square root of the bottom already to give me 2a. Then, to solve for x, we merely move b over 2a to the other side, and, how convenient, our fractions already have like bases. So we combine the numerators, and we have the quadratic equation in a nutshell. So that's where it comes from. Completing the square is what we owe for this wonderful formula, and that's all that I have to say in this video. Thank you very much for your patience. Have a great day, and good luck with your studies. I'll see you in the next one.